Hello, welcome to Econometrics Melody. In this video, we will discuss about the coefficient of determination. We also call it as RE square, and this is also the measure of goodness of fit of a model. In our preceding video, we had divided the total variation in dependent variable as the variation explained by the independent variable and the variation that remain unexplained. Sum of the square of total variation is given by this expression y transpose m0 y, while the sum of the square of the variation explained by the regression or the independent variable, this is given as beta transpose x transpose m0 xp, e transpose e, this is the sum of the square of the residual, that is the unexplained variation of dependent variable y, and these are their respective degrees of freedom. And in our earlier videos, we had seen that the sum of the square of the residual, when we add a single independent variable, then the sum of the square of the residual, it decreases by either by this factor or by these components. So the coefficient of determination or the goodness of fit of a model, this is actually the square of the correlation between the dependent variable and the fitted values, and the measure of it is given by the sum of the square of the variation explained by regression divided by the sum of the square of the total variation, and the sum of the square of the variation explained by regression, this can be also written as the sum of the square of total variation minus the sum of the square of the variation that remain unexplained, and this can also be written as 1 minus. And if we substitute their value, therefore the coefficient of determination, this is given by, and the value of coefficient of determination, it ranges between 0 to 1, and this is actually the square of the correlation of the dependent variable and the fitted or the predicted values from the OLS regression model. Now let us calculate the coefficient of determination when we add a variable to the model. And from our earlier videos, we know that if we add a single variable z, that is the independent variable z, in the model, then the sum of the square of the residual term, it decreases. We know this relationship. And before that, let me explain the situation once again. We have a model, linear regression model, where the dependent variable is y, and all the independent variables along with the constant term is represented by this matrix X. And to this model, we are going to add an additional variable called z. And we have already seen that the sum of the square of the residual when we add a variable, that is less than the sum of the square of the residual when we don't add a variable, and their relationship is given by these expressions. And for our purpose, let us pick this relationship, and let me write it once again, where r2 square yz, this is the partial correlation coefficient between the dependent variable and that additional variable after parcelling out the effect of x. Now to this expression, let us divide both the sides by the sum of the square of total variation in the dependent variable y. So this is the sum of the square of the residual when we add an additional variable, this divided by the sum of the square of the variance of the dependent variable. So this is equal to, from this relationship is the coefficient of determination, this is equal to 1 minus sum of the square of the residual divided by the sum of the square of the deviation from mean of the dependent variable. So this should be equal to 1 minus r square when we add an additional variable z, 1 minus coefficient of determination when the independent variables are x and z. Similarly, this expression is equal to 1 minus r square, that is the coefficient of determination when we have only x is the independent variables, minus again we have 1 minus, because E transpose E divided by Y transpose M0 Y, this is, if we operate this relationship, we get it is 1 minus R square, and we have X is the independent variable. So let us operate it, and here we need to write minus. So on both the sides, plus 1, cancel out. Let us take minus common from both the sides and cancel it. We are left with and from here, let us take the square of the partial correlation coefficient between yz common. So we are left with 1 minus This is the coefficient of determination when we add an additional variable z to the model where x is the independent variable. So this is equal to the coefficient of determination when we have x only is the independent variable in the model plus this sum term, and the square of the partial correlation coefficient between y and z, this is positive, and the coefficient of determination of x when x is only the independent variable, this also ranges between 0 to 1. So when the partial correlation coefficient between y and z, it is, if this is equal to 0, then these two terms are equal, and if this is not equal to 0, then when a variable is added to the model, then the coefficient of determination, it always increases. And now in order to check this situation, let us calculate the adjusted R square, that is the adjusted coefficient of determination. And to these sources of variation, actually we divide it by their degrees of freedom in order to calculate the adjusted R square. So this is our R square, therefore our adjusted R square, this is equal to 1 minus, and for the sum of the square of the error, the degrees of freedom is n minus k divided by, and the sum of the square of the deviation from the mean of the dependent variable, so the degrees of freedom is n minus 1. And if we operate it, this is equal to 1 minus, and let us collect the degrees of freedom on one side, and from this relationship, if coefficient of determination is equal to 1 minus E transpose E y transpose M0y, then E transpose E y transpose, this can be written as 1 minus R square. So this is equal to, this can be written as 1 minus R square. So the coefficient of determination R square will always increase if we add an additional variable, but adjusted R square, it may not necessarily increase when we add an additional variable to the model. So it depends on the t-score. Let's say if a t-score of a variable z, if it is greater than 1, and if we delete the variable whose t-score is greater than 1 from the model, then adjusted R square will decrease. From this expression, we have derived this, and to derive this result, we have used this relationship, and we have divided both the sides by y transpose M0y, that is the sum of the square of the deviation from mean of the dependent variable, and is R square, this is equal to, therefore, and we have substituted the value of this by 1 minus R square according to our requirement in these expressions. And once again, so when we add a variable z to the model, then the coefficient of determination will always increase, but the adjusted R square will decrease if we delete the variable whose t-score is greater than 1. But if the additional variable has its t-score less than 1, and if we delete that variable, then the adjusted R square will rise. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.